As we get started, let's review over just a few things we began looking at yesterday. Started talking about a series, and a series is not the same as a sequence. A sequence, remember, is just those numbers that follow a pattern, that follow an algorithm, okay? But a series is more specifically the, anyone, sum or the total. The word I want you to think is the word sum, but it's the sum of the numbers in the series. So again, when you see or asked about a series class, we're not just finding numbers, but we're finding the sum of those numbers. We use a summation notation, and it's a Greek letter. What is that Greek letter, class?
Sigma.
Sigma. So some people have said it kind of looks a little like a Z or an E or what. Anyway, it's a sigma. It's the Greek equivalent of an S, I suppose. And we have, instead of an algorithm, we have what is essentially the same thing as an algorithm, but we call it, in summation notation class, the argument. Okay, so it's not an algorithm in the series, though it functions mostly the same way. Class, we call this the argument. I'm surprised some of you forgot that. And then the A sub I means for all of the terms that are in the sequence that we're summing together or adding together. And we're going to start with term number blank, and we're going to go up to term number blank. Well, we're going to start by identifying the smallest value we will plug in. That smallest value, class, is referred to as the lower bound. Oftentimes, it's going to be a 1. Okay, so for now, it's going to be a 1, and I'll show you later how we can adjust that. But for now, starting with a 1, and we'll go all the way up until we get to the ending number, n, and this number is referred to, class, as the upper bound. Okay, if we choose later not to start at 1, we would just represent this m, because m comes before n. That and somebody really hated Maddie when they picked these letters. But anyway, so this is our notation, and when you see the sigma, you know you're being asked for a series, meaning the sum of the numbers in the sequence. I gave you a formula yesterday to write down for a constant series, the summation or the series of just a constant from 1 to n. And it was a really, really easy formula to use. What do, class? Just multiply c times n. So this was the first series formula on your formula sheet. We started that sheet yesterday. We'll add a couple more today. But this was your first formula. Otherwise, you just kind of figured out the series, and the homework largely just had you figuring out the series other than those last two. So we're going to have your homework out books open to page 460. Homework out books open to page 460. And you did numbers 1 through 6. Page 460, numbers 1 through 6. Oh, you took the time to work it out? Okay, well, you know, I mean. All right, so number 1, we were given the series from 1 to 7 for 3i minus 2. Now, what that means, class, is we're going to plug in for the I, the number 1, and we get a value. Then we plug in the number, and we get a value. 4. Because we're plugging it in, right? So 3 times 1 is 3 minus 2 is 1. 3 times 2 is 6 minus 2 is 4. Then we plug in a 3, and we get 7. Do you notice a pattern? What's the next number going to be? 10. And that goes all the way up to 7, so we should have 7 values plugged in. Or you could check 3 times 7, 21 minus 2 is 19. But since it's a series, I don't just keep these numbers. Class, I find the sum of the numbers. So we're going to add all of them together. And what do we end up with for our total, class? 70 ends up being the sum. How many had 70 for the sum? Questions on that? All right, let's take a look at number 2, where we had the series from 1 to 5 for 4 plus I. Again, we're going to start by plugging in 1, and we get 5. Then we plug in, and we get, and we plug in, and we get, then, okay, and all the way up till we plugged in the 5, right? And then we simply add all of these together. And what do we get for the series of 4 plus I from 1 to 5, class? 35 is correct. How many have the 35? So far the series not blowing anyone's brain. All right, look at the next one. We've got the series from 1 to 6 for I fourths. So my first value class is 1/4, then now the only saving grace here is at least they all have a common denominator. At least I wasn't the denominator. So we had 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, and we end up with how many fourths? 21 fourths. And I'm just going to leave it that way. Not that it would be wrong to say 5 1/4 or even 5.25. I like 21 fourths better. How many have 21 fourths? 4, number 3. All right, questions? Is that a question? 5 1/4. Yeah, that's a perfectly fine answer. Okay, did you have the 1/4, 2/4, 3/4? Okay, so just an addition error then. All right, and then let's see, number 4 seems like equally regrettable. We've got a 3i over 2 for our argument. And again, we plug in the 1 class, we get 3 halves. Then we plug in the 2 to get 3 or 6 halves. I'm going to go and leave the halves for sake of ease in adding. Then we plug in the 3, we get 9 halves. And then we plug in the 4 to get the 12 halves. Now, I suppose if you called this 3 and 6, you could add these 2 to get a total of 12 halves, which would be another 6. And that just adds up to 15. Or you could add all the halves together. You want it with 30 halves, which gives you 15. So a couple ways to get it. How many had the 15? All right, questions on that one?
I had 30.
Okay, you just forgot the halves.
Oh.
Is that right?
I guess so.
All right, questions on that? All right, number 5. Now there's the long way and there's the short way. The long way, of course, is to say the sum of 5 from 1 to 6 is to plug in a 1, and when we plug in a 1 class we get, we plug in a 2 we get, we plug in a 3 we get, we plug in a 4, 5, 6, we're done plugging in. There was nowhere to plug it in, that's why it's always 5, and we add it all together in class and we get. But the quicker way, remember, is to simply multiply c times n. And of course we just get 30, in which case we can do it under our head showing no work at all on paper. How many had 30 one way or the other? Questions? So on the next one, we're not going to write 12, 12, 12, 12 a bunch of times, class. We're just going to multiply 12 times 9 to get 108. How many have 108 for number 6? Questions on that? Questions on that? So do number 8 at your seats. Do number 8 very quickly. The sum, or the series from 1 to 13 of 17. And what do we get, class? 221. 221. So all you had to do on your calculator was multiply 17 times 13. That's all we had to do. Questions? So the first series we're going to memorize, let me emphasize that word again. The first series we're going to memorize is the constant series, c times n. We all good with that one? All right. Next series that we're going to memorize is called a consecutive integer series. This is formula number 4. Formula number 4, so find your formula sheet. Consecutive integer series. A consecutive integer series. I'm going to give you the formula to write down, and I'm going to show you why it works, how it works, and then practically the easy way to use it. Here it is. It's the series from 1 to n for I. Meaning you're going to literally just plug in the numbers all the way up to whatever you feel like. And if you plug this in, the quickest way to find it is to take n times n plus 1 divided by 2. The quickest way to find a consecutive integer series is take n times n plus 1 divided by 2. This next thing doesn't have to be written down unless you want to, but don't put it on the formula page. If you're going to write it down, put it on in your notes somewhere. But let's consider this series from 1 to 4 for I. If I plug in a 1 class, I get 1. If I plug in a 2, I get. If I plug in a 3, and if I plug in a 4, 4. Obviously, we can add 1, 2, 3, 4 class and we get 10. But I want you to notice something. If I add the first and last number, I get 5. If I add the next two numbers, I get 5. I get a pair of 5s, don't I? Now, if I were to use the formula, which this one's so easy, maybe we don't need it, we would say n times n plus 1 over 2. Well, n, class, is the upper bound, or 4, times 1 more than 4 divided by 2. And notice there's the 2 sets of 5. Let's take an odd number just to really make things weird. Let's go with a 7. Well, in that case, we wouldn't stop at 1, 2, 3, 4, class. We would keep adding a 5, and a 7, right? It's just consecutive integers from 1 to 7 all added together, right? Added together because it's a series. Well, notice, if I have the first and last, 8, next two, and then there's half of an 8. This could be true anytime there's odd ending number, an odd upper bound. So I have 3 and a half sets of 8. Well, if we were to plug in the formula here, we would take n times n plus 1 over 2. 3 and a half sets of 8. Though the easier way is to cancel like that and get 28. Or you could actually add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and get 28 that way. But it's faster, especially if you have bigger numbers. Take the integer, 1 more than it, cut it in half. And it's because you're getting half as many of the 1 more sets as you add together numbers. Does that make sense? This one now put in the on the formula page as an example. So the formula page, we're going to do one that we would not want to figure out on our own by addition, and that's the series from 1 to 16 for I. Series from 1 to 16 for I. Again, this literally means you're adding up 1 through 16. Again, it's not a factorial, that would be multiplying 1 to 16, right? That would be a factorial. This isn't factorial, it's just adding 1 to 16, but we're not going to do it that way. We're going to take n times n plus 1 and divide it all by 2. We're going to take half of one of the numbers. And you realize, class, if the integer is even, you can take half of it. If the integer is odd, you'll be able to take half of the 1 more. So you'll always be able to cancel the 2 with one of the numbers, which is great. Because if you add integers, you better get an integer. You better not get a fraction, right? So we'll take half of 16 and multiply that by 17 on the calculator because we're lazy. 136. And if I were to take the time to add 1 plus 2 plus 3 plus 4 all the way up to 16, it would add up to 136. But this is a faster way to do it. Questions on that? That example makes sense too. All right, next formula for you to get in your notes. Formula 5. Is a consecutive squares series, or a series of consecutive squares. Series of consecutive squares. So here the series of I squared from 1 to n. The series of I squared from 1 to n. Here's your formula. N times n plus 1 times 2n plus 1 all over 6. N times n plus 1 times 2n plus 1 over 6. You may want to put a star next to this one because admittedly, this one's a little harder to memorize. And there's not an intuitive way to demonstrate. We can illustrate, but not necessarily demonstrate. Let's take a really simple one, though, and let's consider for a moment the series from 1 to 3 for I squared. You can put this on the formula page as your example. The series from 1 to 3 for I squared. Now, one way to work this would be to plug in 1, then 2, and then 3, correct? From your lower bound all the way up to the upper bound. But we're going to square them each time. So 1 squared, 2 squared, and 3 squared. If you add 1, 4, and 9, what do you get? 14. So we already know the answer is going to be 14. Let's test it out. We're going to start by plugging in the upper bound. 1 more than the upper bound. By the way, this first part is just like the consecutive integers. It's the third part that makes the big difference. We're going to double and add 1. 7. And divide all of it not by a 2, but by a 6. Now again, here's the key. If you add integers, you always get integer. You never get a fraction. If you add squares of integers, the square of an integer is always an integer. So if you add squares of integers, you always get an integer. This must cancel. If you cannot cancel the 6 away, you've done something wrong. It must work. So the 6 and the 3, for instance, could cancel to give me a 1 and 2, and then the 2 and 4 could cancel to give me a 2 and 1 here. Notice the denominator is gone. And I end up with 1 times 2 times 7, which is, of course, which we knew the answer would be. Does that make sense? Questions on the series of consecutive squares. Again, the why it works is a lot more convoluted, not nearly as easy to show, but there we go. Questions on this. So consecutive integers, no square, n plus 1 over 2. If it's consecutive squares, n plus 1, 2n plus 1, and now it's all over a 6. Questions? Let's practice a few of these too. Actually, let's look at an example problem first, and then we'll practice some of these. Page 458. Page 458. And there's an illustration of each of these in your textbook as well. So you've got your formula page. I believe there's an example on each of your formula of each of these for your formula page, but an example in the book as well. Look at the first one, letter A. What is that series there, Brandon? Sure. On the example A at the top of page 458. Very first one, page 458, at the very top, the very first one. Is that consecutive integers?
No.
What is it?
Constant.
It's a constant. Because what do they give us? They just give us a constant. So for a constant series, how do we solve, class? Yep. Just multiply the upper bound by the constant, and class, the answer is very easy, 21. Look at the next one. What is the example B in that set? Michael?
Consecutive integer series.
That's consecutive integers. I for just basic integer. From 1 to 8, we're going to add them all together. So that's consecutive integer. For this class, the formula is n times n plus 1 over 2. Again, n times n plus 1 over 2. So that n is 8 times 9, one bigger, all over 2. Well, let's cancel, right? Instead of 8 times 9, then divide by 2, cancel the 2 and the 8 to get times the 9. And you can literally do it in your head. Make sense? All right, that's what they showed there. Well, they actually did the whole multiplication of 72 divided by 2, but we don't do that. All right, and then the next one, notice that's a series of consecutive squares, as indicated by I squared, integer squared, from 1 to 6. Here the formula is a little more challenging, class. The formula is, say it with me, n times n plus 1 times 2n plus 1 all over 6. Again?
N times n plus 1 times 2n plus 1 all over 6.
All right, so we take the n, class, 6, that's the upper bound there on part C, n plus 1, and then double plus 1, and put it all over, and sometimes it just works easily. The 6 canceled cleanly with a single value. We multiply, we get 91. Now, if you wanted to, you could test it, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And you could, if you wanted a fact check, right? You could add all those together, make sure it really adds up to 91. Does it? Yes, it does. All right, questions on that. Page 460. Page 460. I want you to do number 9 and number 13. Page 460. Do number 9 and number 13. And these are a quick way to add consecutive numbers or consecutive squares. Here, when you just see an I class, that means
Consecutive integer.
consecutive integers. And the formula is n. Good. So my n is? And the n plus 1 is? Trying to thinking ahead of myself there, all over. But we're going to cancel the 2 and the to get. And so it's just 11 times 21, which is 231. We good to go on number 9? Questions? All right, and then this next one, as Abby pointed out, is the same one we just did in the example class. We're going to start with n times n plus 1 times
2n plus 1.
all over,
6.
but that ends up being 6 times 7 times 13 all over 6. And as we just found, class, it's 91. How many also realized what Abby realized? Yeah, that wasn't on purpose. That's just me not paying attention to the example. And the other, just I want you to do 10 to 16 even now. 10 to 16 even. This is a section you cannot survive without a calculator. So, very thankful for a calculator. We have a budding young vocalist in the room next to us. Music is free of charge. If we're violating copyright laws, I'm sorry, YouTube. That song has restricted use. You're not paying the owner anything. I'm glad you're not 3 anymore. All right, Audrey, go potty. Brandon, wash hands. No talking in line, Abby. Maddie, hide your... No, don't really. Yes! I thought it was for that. All right, let's take a look. For number 10, we have the series of I from 1 to 12 are consecutive integers. So class, we're going to start with n or times
13.
n plus 1 or 13 all over 2. We cancel to get, we multiply to get 78. How many is 78 for number 10? Number 12. Ugh. All right. Again, consecutive integers. So we start with 71, which is n, times 72, which is n plus 1 all over. We cancel to get 36. Now, I will say, if the canceling takes work, don't bother. Just multiply and divide by 2, right? But if you can do the canceling in your head, it just saves you one set of keystrokes on the calculator. 71 times 36 or 71 times 72, then divide by 2. Doesn't really matter. What do we get for the answer? 2,556. I'm like, I can't do that in my head. So there we go. How many have that answer? All right, look at the next one. I squared, consecutive squares. So we're going to start with n, which is 22, then 23, n plus 1, then 45, 2n plus 1. Double plus 1 more is 45, all over 6. I can take a 2 out of the 6 and 22, 11 and 3, and then the 3 cancels with the 45, 15 and 1. Now again, for me, this is quick and easy. If you say, I just don't see those things that quick, there is no problem with 22 times 23 times 45 all divided by 6. Get the same answer either way, and it's a big number. And it is, class? 3,795. How many had that? All right, again, only cancel if it's easier for you. For the last one, again, consecutive squares. Start with 13, which is n, 14, which is n plus 1, and 27, which is 2n plus 1, all over 6. Again, I'm going to cancel to get 7 and 3. I'm going to cancel to get 1 and 9, to get 7 times 9 times 13, and we end up with 819. Questions on either consecutive integer or consecutive squares? Feel like we got it? All right, in every case so far, the lower bound is always 1. But does every series have to, or does every sequence have to start at 1? No. So it would make sense that if the sequence doesn't start at 1, that the series or the sum of the terms should have to start at 1, right? Number 6 on your formula sheet. Number 6 on your formula sheet, a partial consecutive series. A partial consecutive series. Partial consecutive series. And this is really, I think, intuitive. Partial consecutive series. So the way you'll see a partial consecutive series as a refresher, you'll have a lower bound that is something other than 1. You'll still have an upper bound, and of course you'll have your argument. Well, let's consider for a moment, let's use it as an example, so maybe leave some space to finish the formula. Either come down and put an example, or next to put an example. Let's take the series of I, but not from 1 to 17, but let's say from 8 to 17. A series of I from 8 to 17. Put this over here. We'll consider for just a moment how this series of consecutive integers could work. I could go 1 plus 2 plus 3 plus blah, 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 blah. 7 plus 8 plus 9, blah, 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 plus 17. Agreed? Okay, forgive the blah, 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 but you get the idea, right? But this summation, this series, doesn't start at 1. It only starts at 8, correct? What I could do is I could get the entire series, get that sum, and then I could subtract all the stuff I don't want. And this way, both series start at 1. Does that make sense? So at your seats, let's imagine for a moment that it's a 1. What is the series from 1 to 17? No. Well, 17 times 18 over 2, right? Use the formula, right? N times n plus 1 over 2, which comes out to 153. So if you were to add all 1 through 17, you're going to get 153. But we don't want the 1 through 7, do we? So now let's also find 1 through 7. What's that summation? Or 7 times 8 divided by 2? 28. If we simply subtract away the 28, it will leave us with what we really want. Does that make sense? And we end up with 125. That's literally what the partial consecutive series is. It is equal to, coming back to the formula now, the series from 1 to n for a sub I minus the series from 1 to m minus 1 of a sub I. We wanted 8 to 17. So I started with 1 to 17, and then I did 1 to 1 less than the lower bound, or 7. Make sense? So the formula itself looks kind of ugly, but it's very, very intuitive. In fact, I want you to write down 3 quick steps. Step number 1, find the whole thing. Step number 1, find the series or the sum of the whole thing. Find the whole thing. Step 2, find the part you don't want. And step 3, subtract. Step 1, find the whole thing. That's what this means. Step 2, find the part you don't want. That's this. And step 3, subtract. And that's how we'll find a partial consecutive series. Look with me at page 459 once you've got that written down. Page 459 once you've got that written down. And at the top of page 459, they want us to evaluate a series of consecutive integers from 5 to 9. Now, admittedly, for numbers this easy, it might almost be easier to just add 5 plus 6 plus 7 plus 8 plus 9. Honestly, because it's a pretty small set of values. But for the practice of using, in fact, let's do that real quick. On the calculator, 5 plus 6 plus 7 plus 8 plus 9. Or if you're really good in your head, you can do it in your head. What?
35.
35? Other people like that number as well? All in agreement with 35? I didn't do the math, I'm lazy. Let you do the math, you got the calculators. All right, so we're going to say the answer should come out to a 35. Okay, so what we want to take first of all is the series from 1 to 9. Then we're going to subtract, class, the series from 1 to 4. Do you see it? We're going to take the whole thing, starting at 1 all the way up to the upper bound. I only want 5 to 9, but I'm going to start by finding from 1 to 9. Then I'm going to subtract the part I don't want, everything that's below the lower bound, which is the 1 to 4 part. So, right here, how should I plug in the numbers for my formula? 9 times 10 over 2, and then I'm going to subtract, how do I plug in the numbers here, class?
4 times 5.
4 times 5 over 2. If we wanted to cancel, we could get 9 times 5,
45.
and we could cancel 4 and 2 to get
10.
2 times 5, which is, and there's our 35. So this method really isn't, again, these numbers were quick enough we could do in our head or in calculator easily enough. But if they weren't pretty numbers, not a hard one to use. Whole thing all the way to the top, from 1 all the way up to just shy of the lower bound, and then subtract the values. Make sense now? So again, it looks ugly. I mean, if your parents were to just look at the formula, they'd be like, oh my goodness, my daughter is so smart, or my son is so smart. It really is just common sense. It looks cool, but it's really just common sense. Make sense? All right, so page 460. Page 460. Let's take a look at number 17. Page 460. Let's take a look at numero 17. And here we have a series from 6 to 11 for 13. Well, we're going to start, class, by finding the series of 13 from...
Are you on 17?
Am I looking at 19? I'm looking at 19. Let's try 17. Series of I from 3 to 7. Okay. Series of I from 3 to 7. Okay. So first, class, we're going to start by finding the series of I from 1 to 7. Then we're going to subtract away the series of I from 1 to 2, which is just insulting, but whatever, okay? So from 1 to 7, how do I plug in the numbers, class?
7 times 8 over 2.
N times n plus 1 over 2. And then from 1 to 2, how do I plug in the numbers?
2 plus 3 over
2 times 3 over 2, and we're going to subtract. Well, again, we could cancel to get 4, so 28. Cancel to get 3, and we get 25. And again, this is one you could do 3 times 4 times 5 times 6 times 7, right? But for the practice of the formula's sake, so when there are big crazy numbers you don't want to do in your head or on calculator, it's easy. Look at number 18. This I don't want to do in my head. Series from 4 to 13 for I squared. 4 to 13 for I squared. So consecutive squares from 4 squared to 13 squared. Start by finding what, Genesis? The sigma is read series. So the series of I squared from 1 to 13. Does that make sense? It's a series of I squared from 1 to 13. Okay, and we need to subtract then. Good, excellent. All right, how many had the same thing, thinking the same thing? All right. Now remember, for I squared, it's not n plus 1 over 2, class, it's n plus 1 times 2n plus 1 all over 6. Okay, so for the first part, we start with 13 times 14 times 27 all over 6. And we need to subtract, start with 3 times 4 times 7 all over 6. So again, you're going to work the whole thing first, divide by 6, get a value. Multiply all that, divide by 6, or you could do some canceling along the way. And I'm going to get my calculator out. Especially if I have my calculator, I better. All right, so I'm gonna just multiply because I'm not feeling the can. And the first number class is 819, and then the second number, I can do that in my head, is 14. So what is the series of squares from 4 to 13 squared added? 805 is our answer. Make sense? Any questions on the formulas that we covered today? Obviously, we have the constant formula, which is just C times N. Thank you. Class constant formula? C times N. Really easy. For consecutive integers, good. N times N plus 1 over 2, and then consecutive squares. N plus 1, 2n plus 1 all over 6. And if we happen to have a partial series, find the whole thing, 1 to the upper bound, find the parts you don't want, everything below the lower bound, and then simply subtract them. Your homework for this evening, for the weekend, I guess I should say, number 1, study and memorize these formulas. Anyone feel like you pretty much have them all memorized already? We use them enough, hopefully that'll help, but do make sure you look over the formulas, make sure you've got those studied and memorized. Also, if you would read over pages 456 to 460, also read over pages 456 to 460. Some of it's re-explanation of what we already did, but it'll help you over the weekend to retain, and also a preview of what's coming on Monday. And then on page 460. On page 460, do 7, 11, 15, 19, and 20. Page 460, 7, 11, 15, 19, 20. We'll take a look at all of this in our next lesson on Monday. Have a wonderful rest of your day. Have a wonderful weekend. And when the bell rings, you will be dismissed.